Hello, everybody. Welcome back at the next episode of Functional Programming 101. And today we're going to talk about interactive programs. But before we start, I want to share a story that I originally heard from Simon Peyton-Jones. Simon Peyton-Jones, everybody should know, is one of the main drivers behind Haskell and also one of the founders of the Glasgow Haskell compiler that we have been using in this course. Here's the story. So in this little box, there is a super powerful quantum computer. It's extremely powerful. It can kind of, break every encryption scheme, known to man. It can, solve any problem. It kind of cures cancer, everything. The only problem is that it has no I/O. So we will never know whether this quantum computer works or not. The moral of the story is that if your program is not able to communicate with the outside world, it might as well not exist. And if you go back to the early days of Haskell, it was actually really hard to have a Haskell program communicate with the outside world. Whereas if you use any other programming language, it's trivial. The first code we all write is hello world, which prints hello world on the standard output. Whereas in Haskell, that hello world was super complicated. First we had stream I/O, then we had continuation-based I/O, and finally, and that's what we're going to talk about today, we have the I/O monad. And with the I/O monad, Haskell has gotten its I/O ports on the box such that it can easily communicate with the outside world. All right, so far we have only written programs that take some input and return a string or an integer or tuple or a list, and we have printed that value on the output of the REPL loop of the GHC interpreter. But what we really want to do is we want to write programs like most programs, like every Java program, like every C# program, like any imperative program that takes inputs from the external world, does something with it, and produces outputs. And in fact, what we want is that it produces output as it's getting new inputs. All right, so we want to produce outputs as we're getting new inputs. So what this program has to do, it has to interact with the keyboard and the screen. So if we look at our program as a function, in some sense now it becomes dependent on the keyboard, and besides just producing output, it also will communicate with the screen. The problem is that Haskell programs are pure functions, which means they cannot have side effect. And maybe it's good to kind of informally talk about what a mathematical function is. Well, that's a complex word. A mathematical function is a function that when you give it the same argument will always give you the same result. For example, factorial. When I give it n, it will return factorial n. When I give it n again, it will return factorial of n again. Now look at a common function that we use in imperative programming. For example, readLine. readLine takes no arguments, or the empty tuple, and returns a string. When I call readLine again, with the same arguments, the same empty tuple, it will return a different string. So readLine is not a mathematical function, and the reason is because it has side effects. So it will return a string, but there's something there that is not apparent in the type. And that's what the I/O monad solves. The I/O monad kind of expresses in the type of a function that this function has a side effect. Okay, so interactive programs, programs that interact with the outside world, have side effects, and we need a way to incorporate side effects in Haskell programs. Now, I don't think that side effects are bad. Actually, they are super useful because, without side effects, it's really hard to write these interactive programs. But the thing is that you have to make sure, again, it's a balance. It's a question of taste, how you use those side effects. It's a little bit like salt or spices in food. You can overdo it and your food is too salty and it doesn't taste well. But if you don't use any salt, your food is also not tasty. All right? So it's up to you as a developer to decide how much side effects to use. But it's never a good answer to say, I'm never going to use side effects. Or it's also never good, the other extreme, to say, I don't care about purity. Okay? That's exactly what shows mastery of programming, that you can decide where to use side effects and where to avoid them. But if I hear you say, we have to program without any side effects, you have not understood the essence of this course. Okay, so as I mentioned, the solution to the problem is to introduce a new type, and we really don't care how this type is defined. For now, we'll just assume it's some abstract type, I/O of A, and this type denotes an action that will perform some side effects, and as a result, will return a value of type A. And maybe a good way to remember the difference is that in Haskell so far we've only used expressions, but we didn't mention statements. Whereas in an imperative language there are expressions and there are statements, where statements mostly communicate via side effects. And in some sense, by introducing the I/O monad, we are also introducing statements in Haskell, or another way to say that is we introduce the notion of actions in Haskell. Okay? But these actions themselves are also expressions, so they can be composed. Let's look at some concrete examples of the I/O monad. Here's I/O of char, which is the type of an action that will perform some side effects and then return a character. And then the most imperative of imperative types, that is I/O of unit. That is a function that only performs the only interesting thing it does is performing side effects. Because it has no real result value, it returns the empty tuple. And in a typical imperative language, this would be the type void. So if you have a function that returns void, in Haskell that becomes a function that returns type I/O of unit. Okay? And void is nothing, or unit, this empty tuple is nothing special. It's just a tuple that has no components. Now that we have this type, and again, we really don't care how the I/O monad is defined, as long as we have operations defined on them. Okay, so this is like a little bit like object-oriented programming. We have a class, we have methods on that class, and in order to use a class, you don't need to know how that class is implemented. You just, use the methods. And that's the same thing here with the I/O monad. And the first operation that we have on the I/O monad here is get char. In a typical imperative language, get char has type unit arrow I/O of char. Unit arrow char, sorry. In Haskell, because we're lazy, we don't need the unit arrow. And so instead, get char is just something that has a side effect and then returns a character. Now, if this would be strict, it would kind of, immediately return the character right there. But since Haskell is lazy, we don't have to have this explicit thunk that defers evaluation. That's another interesting thing. In typical imperative languages, whenever you see a function that has type unit, arrow, something, it means that you're trying to simulate laziness. Here's another example, the function putChar, which writes a character to the standard output. It takes a character and it returns void. It has side effects, but it doesn't return any useful value. And then we have, just like for parsers, we have the action that immediately returns without doing anything. Okay, so it takes a value and it immediately returns that value without performing any further side effects. And then we'll be using the same kind of sequencing that we used for parsers. And again, in the exercises, you will see how this do notation is translated in terms of the bind function. But right now, we'll just use the do notation because it looks very much like traditional imperative code. So here's a function that reads a character, reads another character, but ignores the result, and then reads a third character and returns the pair of those two. So if you remember the parsers from the last lecture, we had more or less exactly the same example here, except that we used the item parser 3 times, and here we're reading a character from the standard input. We can define a function using getChar that reads a string from the standard input as follows. If we read a character, we call that character x. Notice that getChar has type IO of char, and then x here has type char. So the arrow is very similar to the arrow in generators in list comprehension. So there's an IO of t on the right, and then there's a t on the left of the arrow. And that's why we use the arrow symbol and not, say, the equal symbol. Okay, because the type on this side is different than the type on that side. Well, if the character that we just read is the new line, then we're done. So we return the empty string. Otherwise, we recursively read on to read the rest of this character, and then we return the previous character that we read concatenated on the string that we recursively read. So another kind of recursive thing here where we just call this thing itself recursively until we hit a new line, and then we return all the values. Here's an example that takes a string and writes it to the standard output. So if we have the empty string, we cannot do anything, so we just return unit immediately. If we have a string that starts with a character x followed by a string access, we print the first character, and then recursively we print the rest of the string on the screen. This guy here returns IO of unit, so the whole thing returns IO of unit, and everything fits. Now we can define another function that simply combines putString with putChar to write a new line behind it. So we first print the string, and then we print a new line. The beauty of all this is that we can mix and match imperative code or IO code with all the functions that we have defined before, in particular functions over lists, because strings are just lists. So we can imperatively read a string from the standard input, then use regular list functions on that string, and then imperatively, within the IO monad, write this to the standard output. So let's walk through this example. We print enter a string. We read this line from the input, and then we print that that line has so many characters. Okay, very simple. But you see here, you combine, there's an island of purity in the sea of impurity. And this is a perfect way to program. So you have little parts of pure code embedded in a context of impure code. And when we run this string length in GHCI, it will print enter a string, we type a string, and it will tell us that this string has 5 characters. Okay? And note that this thing is only evaluated for the side effects. It doesn't return a useful value, and we see that because it has type IO of unit. This is the end of part 1. See you in a few minutes when we're continuing to talk about the IO unit. Thank you.